If you have 10 kilograms and put it on the scale, you expect to read 10 kilograms. If you have distance of 10 meters and you walk that distance, you expect to measure walked distance of 10 meters. If you have 10 gigabytes of clustered index and you do a full scan of this 10 gigabyte clustered index, you expect to read 10 gigabytes, right? But you may be surprised. And I'm not talking about top scan, you know, top first few rows. I'm talking about actual full scan of all rows. I'm talking about select star from table, where, and then some condition with a column that is not indexed. So it is a genuine full scan of all rows, entire table. What do you think? Will it read all 10 gigabytes? Write in the comments below. Write 10 below if you are certain it will read 10 gigabytes. But recently I had a client and the case with a full scan of a huge table, 250 gigabytes. And that full scan should take minutes, maybe hours, depending on are they pages cached in memory or read from the disk. But this full scan of 250 gigabyte clustered index took only fraction of the second. And it really read all the rows. So how that can happen? How that can be? Let's dig in. Let's explain several things. This is a clustered index, pages of a clustered index. It has a root page, intermediate indexed pages, maybe several more levels of intermediate index pages, and then data pages. So these index pages, root and intermediate pages, non-leaf pages, basically are insignificant. Their number is insignificant compared to the data pages, because this exponential function is like 100 to power on x. It grows exponentially, not 2 to the power of x. It is hundreds, depending on how many rows, how many key values fit on the page. So it can be multiple, 400 on x. So it's really rapidly grows. You will rarely see more than 4 or 5 levels here. So let's say 3 or 4 levels is common here. And the number of pages here is 100 times less than number of data pages. So it's really insignificant percentage of pages. So almost all pages are actually data pages, this here. In these data pages, which are each 8 kilobytes, we have rows. And these rows may fit into page, but if you have a large varchar column or a var binary column, something more than 8 kilobytes, it may not fit into the page. And what SQL Server does is this. Let's see one row, example of one row with data types. So you have one row and an integer, which is a fixed data type of 4 bytes. You have a date, which takes 3 bytes, bit, which takes, this is yes, no, or 0 and 1, which takes 1 bit, and unique identifier, which takes 16 bytes. It's for global unique identifiers. So these are all fixed data types. Fixed data types. They always take the same space, no matter what value is inside. Now we have variable length columns, like varchar. Varchar 100. It can take variable amounts of characters up to 100 characters. Or nvarchar. It can take variable number of characters, but up to 4000. By the way, you cannot specify more than 4000 in nvarchar, because it would take 8000 bytes. Each character takes 2 bytes. So this would take 8000 bytes, and that's the maximum length you can put on the page for any value. So that's why var binary, maximum value you can specify is 8000. But don't specify more than you actually need, because that affects memory allocation. So you should specify something that is really normal for your data. Don't specify everywhere 8,000 or everywhere 4,000. Specify how much do you actually need, 100 or whatever. Then we go to this max types, varchar max, var binary max. There's XML, it can be XML too. There are also some older types like image, text, but you shouldn't use those. These are deprecated. So these are large data types. Up to 2 gigabytes can each value be. But how can you fit those into one page? It definitely can happen that that row cannot fit into the page. So what happens? If variable length data type cannot fit into the page, if the value cannot fit, then a separate page is allocated, which is called a row overflow data page. And that page then stores this value, and 24-byte pointer is created instead of the value to point to that page. It's out of row. It's in row overflow. So it is placed out of the normal page. And that, for a single row, you can have multiple values in such a way. So for example, in this example, 3 columns have a separate page for their value, which couldn't fit into the normal data page in row. They couldn't fit in row, so they allocated extra 3 pages for these huge values. And that value, that row can take maximum 8060 bytes together with all the overhead, etc. Basically, value can be maximum 8000 bytes. And what if this max type cannot fit into the page? If they cannot fit into the page, then they are allocated also on a special page types which are called LOB data. So LOB data pages are also like an array of pages up to 2 gigabytes. So it's like a chain of pages. So you get also 24 bytes pointer from your column. Instead of the value, you have this pointer that points to the array chain of pages which actually contain the value you wanted to store. So each value can be up to 2 gigabytes. And that's the picture how your data can look. We can see it in the summary. So you can have in-row data. In-row data is a normal data page with all the fixed length values. And this is our row. This red thing is our row. But for the variable length values, if they cannot fit and they are, let's say, not a max, not a LOB types, they will allocate row overflow pages each and be stored there. And for LOB data types, which are max data types, array of LOB data pages will be allocated to fit them. Of course, if these values are small and they fit into in-row page, in-row data page, they will fit there. They will not allocate any extra pages. Everything will fit in normal in-row data. But if you have large values, larger than can fit into the page, you will see these extra overflow allocations or LOB allocations. Okay? In my example on this client, table had majority of data, majority of gigabytes placed into LOB data. So out of 250 gigabyte, probably 249 gigabyte were allocated to these LOB values. So this in-row data was actually super small. And when you do a select star, this select star, although you are mentioning star, all the columns, but in where condition I had these values which are placed in row. So to test each row, SQL Server did read only in-row data. and never read overflow or lob data pages. Always it tested only in-row pages, which was enough for that filter, and no row was satisfying that filter. So 0 rows were the output, and pages read was like nothing. I mean, it was like a blink of the eye. So full scan in blink of the eye read only 0.1 gigabytes, something like that. Super small amount of data. So let's look at the demo. So here we have a table of cars, which has CarId. CarId is integer identity and clustered primary key. By the way, primary key can be non-clustered. You can have separate different clustered index from the primary key, which can be non-clustered. Insurance policy ID, which is also integer, then some other data, which is fixed length data type, 42 bytes, and car description, which is variable length data type, but up to 8,000 bytes, and lob data type, which is NVARCHAR max, so 2 bytes per character, up to 2 gigabytes. And I inserted 10,000 rows there, but in description it was like 8,000 bytes stored. In CarDescriptionLOB it was much more. It was 200,000 bytes, 200 kilobytes, let's say, per value. So it's quite a large lob value. And if you want to see how it looks, it is 8,000 bytes for description, and for lob it is 200,000 bytes per value. So if you double click here, then Ctrl F1, and you will see some details, because I installed a special procedure, SPXDetails. You can download from the link below. In the description of the video there is a link you can download that stored procedure, map it to Ctrl F1, and you will have same functionality. So you just press Ctrl F1 and you see the details of this table. So you can see it has a primary key clustered, 10,000 rows, 2 gigabytes. And if you want to see more details, you can press Ctrl F1 and then again Ctrl F1. It is like a double click. Now you see more details, additional information. So you can see that this index, clustered index, has only 1 megabyte in row. Overflow is 80 megabytes, but in lob pages, in lob data, we have 2 gigabytes, much more. So majority of this table is in lob pages, lob data. That will explain later results. So let's see. If we run this select star, where insurance policy ID is 1, 2, 3. So this is not index count. None of this is indexed. We have only index on CarId. So if we run this, it will be a full scan. So you can execute. It is a full scan. You see clustered index scan. All 10,000 rows are scanned. But if you read here how many pages are read, 147 pages, nothing more, no lob pages are read. So only 147 pages. That's why execution time is basically 1 millisecond. CPU time is 0, so it's super fast. Although it is a full scan, it is a super fast full scan. Although the table has 2 gigabytes, this reads only a fraction of a megabyte. Super small, several kilobytes basically. Then if we run this select, execution plans looks the same, identical. It is a full scan of 10,000 rows. You cannot differentiate anything here, but you can see in messages you have 147 logical reads, which is in row data, and lob logical reads 10,000 pages, which is row overflow basically. It is a row overflow. And that took 16 milliseconds because we are reading more. We are reading more pages. Much more pages than before. Much more. So let's do another query, which is on lob column. Execution plan is almost identical. You can see a full scan of 10,000 rows. Only additional filter operator is here, like a predicate. But basically, essentially, it's the same execution plan. And in messages, we can see 107 in-row pages are read, plus lob logical reads 40,000 pages. So much more pages, because we are reading lob pages, not just in-row data, also lob data pages. And the last one is almost the same query, but look at how long it takes. Query is still running. Query is it takes much more time. But why? Why this query takes so much more time? Well, because to test this condition, SQL needs to read only first page. At the beginning of the page is value, everything is A. So no, X. All the values are X. So to test equals to B, immediately SQL sees on the first page that it's not equal to B and discards the row. So it needs to read only one page, let's say, per row. Small amount of data for each row. But here is like percentage B. That means it ends with B. So to test does it end with B, he needs to read all the pages. And to read all the pages, it is many more pages. So you see, it took, execution plan is basically the same, full scan. And 10,000 rows, so you cannot differentiate anything here. But if you measure how many pages, 147 in-row pages and lob logical reads 1,460,000 pages. That's a lot of pages. So it read a lot of pages, a lot of CPU time, almost a minute of elapsed time. Very long time. So if you look at the execution plan, in all 4 cases, we had almost the same execution plan. It is a full scan. But all 4 full scans are very different. We had a full scan that is blink of the eye because it reads, it tests for a column that is in row. And where we tested the column that is in row overflow, it was much slower. But when we tested for a column that is placed on the lob pages, that was very much slower. And when we tested a lob column, when we need to read all the lob pages, it was super slow. So a full scan can read either super small insignificant amount of pages, let's say in-row pages. If you have only small amount of in-row pages, full scan will be super fast. Or it can read a bigger set of pages, like overflow pages, some overflow pages that are needed to filter the rows. Or it can be super slow if you read all the pages, even including lob pages. So full scan is not the same. Every full scan is not the same. So full scan looks the same, but it's not the same. They are very different. Full scans are very different, and you cannot differentiate them in execution plan. You need to measure and look actual number of pages that are read. Thank you so much for attention. My name is Vedran Kesagic, and see you in the next video. Bye.